One of the concepts that some people have challenges with when they're taking their first amateur radio course is this idea of amplification. So in the next few minutes, we're going to go into that concept and hopefully clear up any confusion that you may have. The first thing is let's think about what amplification is. It's a process of converting a small signal into a larger one. But the small signal doesn't actually change. And this is a concept that is a bit difficult to understand at first because we oftentimes think that the small signal is going to be converted into a larger signal. It's going to be boosted, which is correct in one level, but it's also not accurate in another level. So let's go into a little bit deeper into that. The factoid is, the actual key fact is the small signal, the input, is used to control a larger current or voltage source, which is the output. And specifically, let's use this water flow analogy here. We have a large water tank filled with a large volume of water, and this represents a power supply, a battery, some source of voltage and current. And then we have a valve that's controlling the flow in this water pipe. And the valve controls the rate of the flow, as you can probably imagine, just like a spigot on your faucet. The valve will span from fully open, which is 5 force points in this example, which is maximum flow, to completely closed or 0 force points, which means that nothing comes out of the pipe. So if you look at the maximum flow in the pipe is 800 force units, and it takes 5 force units to turn the valve from fully closed to fully open. So that input, what we're doing with the small valve, is where the small signal is going to be applied. And what's going to happen is it's going to change the output of the larger signal, the larger amount of fluid here. So again, the value of the input signal changes the valve's position, and this causes a proportional change in the source's output flow. So again, the small signal is used right here at that valve. It's the thing, let's say electrically, if we want to use that, or our hand is turning that input, that valve. And in the case of the small signal, it is doing work right here, and then it's gone. It no longer exists. Once that small signal enters into that location and begins to manipulate the valve, it no longer exists at that point. Once it's actually been used, work has been accomplished by it. What's happened is the small signal becomes reproduced in the higher flow. So we are not taking the original signal and giving it more energy. What we're really doing is using that small signal to control the larger source of energy, and then the small signal's changes are being reproduced in the higher flow's output. Let's take a look at this a little bit more. And let's ask the question again, what happens to the larger flow when the small signal changes the state of the valve? And again, the valve has a span of 0 to 5 force units, and the output has a span from 0 to 800 force units. So let's start by having the valve fully open. And you can see we have a 5 force units, which is fully open, which is creating 800 force units in the output of the pipe. Now we've closed the valve by 0.25%, by 25%, and now we see that the amount of flow on the output has dropped proportionally. Remember, we've gone from 5 to 800, and now we're going from basically 75% of 5 force units to 75% of 800 force units. And now we're going to close that valve down to half level, which means the force is now at 2.5 force units on the input, and now we are a little over 400 force units on the output. We further close the valve, and then we close the valve again, and now we can open the valve a little bit, and you can see that the signal, the small signal, the input signal has been reproduced in the output signal. The small signal has been now proportionally affecting the output signal, which is at a higher amount of force available. And that's the key. The small signal is gone. It's actually been used to adjust the flow. It's done its work. It's gone. And what's happened is we've had a proportional change in the output, which is a higher current or voltage source. And so if we look at the ratio of the maximum input signal to the maximum output signal, we can see that it has got a maximum gain of 160 That is the key here. 800 divided by 5, we have a maximum gain of 160. So we have basically multiplied that small input signal by 160. And that's the effect that an amplifier has, is it has the ability to have that small signal control a larger current source, and by controlling the larger current source proportionally, we are now effectively putting a gain on that signal. It has been, excuse me, boosted, relatively speaking, in the output signal. So again, we have taken the effect of that valve, that small input signal, and multiplied it by 160 to get the change in the larger source of flow. So we can look at understanding this also by looking at bipolar transistor, and we're going to use a water flow analogy to look at that. And we're not going to go into detail on how that works, but just understand that that is a transistor is used as an amplifier, can also be used as a switch. And this is an NPN bipolar transistor. It has three terminals. One is the base, then there's the collector and the emitter. In the configuration we're going to look at, the base is where the small signal comes in. That's the top diagram. And the collector is where the positive side of the voltage power supply is coming. The negative side is where the resistor is located and where the emitter connects to the resistor. And the resistor is going to be the load of the circuit. That could be a speaker, that could be another stage, whatever you want to connect it to. So we have the small signal now controlling the base of the transistor. We have the large source of current attached to the collector. And we need about 0.7 volts DC for this type of transistor to conduct from the base to emitter. So just so you know. So we look at the water flow analogy down below that. We have two troughs. One bigger water flow trough, which is from C to E, and then one smaller trough that's going from B to the channel that's C to E. And if you look closely, you'll see that there are two gates. And the gate on the B trough is connected to the gate on the C trough. And you can see that the gate on the B trough is relatively small compared to the gate on the C trough. And because they're connected, if you can think about it, as the B trough opens, it starts to lift the C gate, and then the flow of water will then flow from C to E. And so that's exactly what's going to happen, is the greater the flow in the path B, the more flow is allowed from the trough C to E. And this is, again, the small signal is controlling a larger flow. And as the changes in small signal are changing that, for lack of a better term, that water gate and the B trough, we see the flow C changes in proportion to the flow B, creating a replacement for the small signal with a bigger one, and that's amplification. Now, we have different types of amplifiers that do different types of jobs for different kind of practical applications that we want. And when you decide which amplifier you're going to use, there are trade-offs that you have to make. One is efficiency and heat dissipation. The next is linearity, also called fidelity. And fidelity is the degree of exactness with which something is copied or reproduced. So if you have a very high linearity amplifier, it means that the proportional change in the input signal to the output signal is exactly matched. Whereas if you have low fidelity, it meant that you would have an input signal that didn't quite match the output signal. Now that's okay in some situations, in other situations that's not good. So these are the kind of major class amplifiers that are available. Class A has high linearity, but it's less power efficient. It's a device that is always on, it doesn't have an off state, and therefore it uses more power, but you're not getting the effect of the power at all times, because there may not, when the signal is zero, the amplifier is still on. Versus a class B, which is a two-stage push-pull device. It's more power efficient, but it has less linearity and more distortion. So what you gain in efficiency with a class B, you lose in some of the linearity. And then we have a class AB, which is kind of a combination of the good parts of A and the good parts of B. There's less distortion in class B alone, and it's more power efficient in a class A. And so there's a trade-off between that linearity and fidelity versus power consumption. Power consumption is different than power output because remember, it's going to take more power. The circuit's going to consume more power than it's actually going to put out because that's in the process of doing this work, things are converted to heat, for example, and not useful work versus useful work being like running an amplifier or going out to an antenna for transmission. And a class C is a high power amplification of a sine wave where linearity is not important for such modes as Morse code or FM. And of course there are others, but these are the major types of amplifiers. And again, we choose the right amplifier based on what we need given efficiency, heat dissipation, and fidelity. So amplifiers are also designed to have a specific frequency response. And audio amplifiers are optimized for reproducing the frequencies of human hearing, 20 hertz to 20,000 hertz or 20 kilohertz. And so what you want is to have the best reproducibility in the hearing range. And where you see on this graph is that the best reproducibility is in the bandwidth that's indicated here between F of L and F of H. If it's below, and this let's assume it's below 20 hertz, we see the amplifier rolls off very quickly. It doesn't handle those areas very well, and so the gain drops very quickly. And conversely, if you're above the F of H, the amplifier isn't going to handle higher frequencies as well, and therefore it's not going to be as efficient and it's not going to reproduce as well, and so therefore the power level it outputs from the amplifier will drop down. And this is true for RF amplification as well as I said audio or AF, audio frequency amplification. Every amplifier is designed for the specific frequency response. And here's an example of a class AB audio amplifier using bipolar transistors. We see two transistors. In this case, they're not using the traditional schematic resistor symbol. They're using just the R with a rectangle. And we have two transistors that are operating. One is going to be operating during one half of the cycle of the sine wave, and the other will operate on the other half of the sine wave cycle. And the capacitors on V in and V out are what are called DC decoupling capacitors. So any DC that is in these lines will not be passed to the next stage, so that only you get the pure signal out. So we take a small signal, as you see on the left side, that's going into the base of one of the transistors in this example, and it's controlling a larger current flow coming from the power supply VCC and going to control R sub E, which is going to be where it's going to result in a larger voltage coming out of V out. There's also a class AB RF amplifier using field effect transistors or FETs. Very similar approach. We have two FETs. One is going to be operating on, the other is going to be operating when the other one is off, etc. We use here two transformers to do impedance matching and to produce isolation between the input circuit and the output circuit. And the other source is that there are operational amplifiers, analog integrated circuit devices, that you can arrange as a B amplifier, Class C amplifier, or Class A, etc. amplifiers as well. And those are integrated devices that have much more amplifier gain because they have many more transistors or field effect transistors built onto them. The output of a modern radio is basically what are called MOSFETs, or a type of field effect transistor that is able to deliver the higher powers necessary for many of our modern transceivers. One of the things that can happen with an amplifier is clipping, and that's when the amplifier becomes overdriven. And clipping occurs when the amplifier is pushed to create a signal with more power than the circuit can supply. Anything over this value is clipped and lost. That's distortion. And so if we find a situation where we find the output is clipped, what we have to do is throttle back the input so everything stays aligned with what the capabilities of the amplifier are given its power supply. So what is amplification? Well, it's the method of using a small signal to control a larger source of current or voltage such that the result is a higher output power signal that looks like an aspect of the original lower power input. Again, the small signal is actually disappearing in this process. What's happening is we're replacing it with a higher power signal that is proportional to the input signal, and that is amplification. So if you have any further questions, feel free to email me at w7dao@arl.net, and I'll be happy to answer those questions. Thank you very much for listening.